Okay, let's do the review here. So first one is a distribution of scores is approximately normal with a mean of 78. So mean of 78, a standard deviation of 8.6. Which of the following equations can be used to find the score? Okay, so you got to remember the z equation. So z, this I feel like was one of the big issues. So it's the sample mean um, minus the population mean, I think, basically over the standard deviation. So in this case, so how do we figure out the z-score, right? We don't know the z-score of this guy, right? So let's see. So 33% above which 33% of the score. So there's some value over here somewhere. I don't know what that is, where 33%. So this is like 0.33%. So I'm trying to find out what that would be. So let's go to our calculator. So go to menu. So I'm pretty sure it'd be inverse norm. So 6, 5, inverse norm. Right, so if we put in, so the way this command works is you put the area to the left. So if there's 33% to the right, there'd be 0.67 to the left. If I put in the mean of 78 and standard deviation of 8.6, I think it'll just give me the answer. But we don't really need the answer. We need, but that's actually the answer. We need the z-score. So let me redo that because we got too much information. We got the answer. 6, which we could get if we need to use that. So let's just put in the 0.67 here because that's the area to the left of the point we want. I want to find the z-score. So if we do that, we get a z-score of 0.44. So the z-score is 0.44. When you do inverse norm, if you put in 0, 1 for default, it gives you a z-score. Well, we don't know x bar. We do know the mean is 78. We do know the standard deviation is 8.6. And I was going to solve this. And by the way, if you do solve it, you get 81.78. Just to show you that's true, if you, let me go back to the calculator. I think this would be true. So if I do 0.44 equals x minus 78 over 8.6, comma x, you get 81.78. So you do actually get the answer we got. It was just they didn't want the form of the answer was different than what we expected there. But inverse norm is your key to that one, but also just using z-score appropriately, finding the z-score of that value. So what that means is it's 0.44. I didn't draw this very much to scale. One standard deviation is over here somewhere. That's like one standard deviation. This is 0.44, so it's just a little bit above the 78 there. Because one standard deviation, it's 0.44 above the mean there. Okay, a lot of folks missed this one too. This is number 22. So the distribution of long jump distances is approximately normal with a mean of 18.5. So 18.5. Standard deviation of 3.2. Two students competed. Josh's was 0.5. Standard deviation is below the mean. So let's find that. So what's 0.52 standard deviation? So we know one standard deviation, one full standard deviation is 3.2. So what would 0.52? So 0.52 times 3.2. So 0.52 standard deviation is 1.664. It's that far below the mean. So 18.5 minus that. So the first guy is sitting at 16.836. That's, I guess, Joshua maybe. Yeah. Okay, and the second guy was at 18th percentile. Okay, so we've got to find what the 18th percentile. Again, this is a good case for inverse norm. So let's just let calculator do everything for us here. So menu 6.5 inverse norm. And that is to the left. It said it was the 48th, was it 48th? Yeah, 48th percentile, so 0.48. Let's put in the mean of 18.5, standard deviation of 3.2, and it should give us, so that the next guy is at 18.33, and that's Mateo. Then we answer the question. Joshua's distance was at the 30th percentile and was less than, so Joshua is definitely less than Mateo. So now I guess we need to figure out what percentile score that is, right? So if you think about Z, so Z equals 16.8 minus the mean of 18.5 over standard deviation of 3.2. Let's do that to find the Z, which is the percentile there. So 16.8 minus 18.5 over 3.2. Well, that gives you Z-score, and we could get the percentile from that, I think. So let's see. So, oh, we don't need to do that. I could have done norm CDF. What am I doing? So norm CDF, this guy. We want to find out how much of the data is below 16.8, right? So let's go to norm CDF. So menu, whoops. So menu 652, I think. Lower bounds negative infinity, upper bounds, we said 16.836. And mean is 18.5. Standard deviation is 3.2. That's pretty close to 30 percentile. Yeah, I'd say that's 30th percentile. Yeah, that's good. So it's A. So 30th percentile. That one was good. We got lucky the first time. We probably could eliminate answers and got it quicker, I'm guessing. Okay, so number 8. Asha's financial literacy project involved comparing the annual sales of companies in Canada and the United States that produce software using a ratio of 1 Canadian dollar to 0.75 United States dollars. She converted all, so she's multiplying to convert, right? All it from Canadian into United States dollars. She's multiplying everything by 0.75. Which of the following values will change? Which of the value will be equal, so it won't change. So the median is going to be multiplied by 0.75. Measures of center multiplied are affected. Standard deviation measures of spread. When you multiply, are affected by that. They're not affected by adding and subtracting, but they are affected by multiplying. Mean is a measure of center, affected by multiplying. Measure of spread, affected by multiplying. All those are affected by multiplying. This means the Z-score. Z-score is not affected by multiplying, right? We can change, different scales. Z-score is not affected by any of that. So that's what it is. So a bunch of folks missed this one. Athletes in particular sport are classified as either offense or defense. Distribution of weights of the athletes is approximately normal, centered at 200. So there's 200. So I don't know, there's something normal there. Distribution it ranges from 150 to 250. So 250, 150, looks something like that. Distribution weights of the defense is centered at 300. So there's, 300, and it goes from 250 to 350. So something like that-ish. That's a really bad drawing, but what would describe it? It's definitely bimodal, right? You've got offensive and defensive guys are largely different weights. Number 7, grocery store receives deliveries of corn from 2 farms, one in Iowa, the other in Ohio. Both farms produce ears of corn, so mean weight of 1.26. From Ohio is 0.01 greater than that of the other one. Randomly selected ear of corn from Iowa weighs 1.39 pounds, has a standardized score of 1.645. So using the Z equation, 1.645 equals, I guess it had a sample of 1.39 minus 1.26 over standard deviation. So I'm going to solve using a calculator because this is stats class. You don't have to do algebra. So solve menu 3.1 if you need it. 1.645 equals 1.39 minus 1.26. Sorry, can hardly read my writing there. Over, I'm just calling it x, comma x. So we get a standard deviation of 0.079. And it says that's for Ohio. Wait, yeah, so Ohio has a standard deviation. So this was Iowa. Ohio has standard deviation that's 0.01. So if I add 0.01, so 0.089, I believe, is standard deviation of that guy. If ear corn in Ohio weighs, how many standard deviations from the mean weight is respected to Ohio? So Ohio has, so Z equals, I don't think we know Z, right? So we know it's 1.39 minus 1.26 over 0.089. See if this gives it to us. Last time I was wrong about the Z-score. It wasn't what we needed. Let's see if it is. 1.39 minus 1.26 over 0.089. 1.4607. 1.46, I know it's one of these. That's positive, so it's above the mean. So it's B. Oh, worked out nicely. Number of siblings was recorded for each student, a group of 80. The summary stats are to the right there. Love it. Skewed right. Maybe an outlier. An outlier is often described as a number that's more than 1.5 times interquartile range. So the interquartile range is Q3 minus Q1. So IQR here is equal to 3. So 5 minus 2 is 3. So 1.5 times that is 4.5. You can do that without a calculator if you want. So I need to go Q3 plus, just plus, not plus or minus, plus 1.5 IQRs. Well, we just said 1.5 AR is that, so Q3 is 5 plus 4.5, 4.5, which is 9.5. That's our upper, yeah, we're, so is that an outlier? So 18. It definitely has a couple of outliers there. The one at 10 and 12 are both outliers. It has 2 outliers. Only one has 2, so it's one of those. It's skewed right, so that means the median is somewhere here in the middle, and the mean is going to be to the right of that. I'm not sure about the exact spots. I didn't pay attention to that, but it's the mean, because it's skewed to the right, the mean is bigger than the median, which is all I think I needed to know. The median is less than the mean. That seems correct. And the distribution has 2 outliers. Okay, so we're to unit 2 now. So these were the most missed questions for unit 2. A penalty kick involves 2 players from different teams, the shooter and the goalie. During the penalty kick, the shooter would try to score a goal by kicking a soccer ball left or right. They're always trying to guess if it's left or right. To prevent the shooter from scoring a goal, the goalie will also guess. Well, I guess the goalie is more guessing. The person who's kicking it tries to make a good decision there, I guess. They're going left or right. The following table summarizes all the actions there. Which of the following indicates an association between the shooter's choice of direction and the goalie's choice of direction? So marginal relative frequencies means the margin at the ender. So at the end, for the shooter and the goalie are equal. So let's just try that. So what is, so this marginal would be 212 divided by 372. And this marginal would be 165 divided by 372. For the shooter and the goalie, if they want to go left, I'm sorry, I did that. So I don't need a calculator to see those two are not equal. The marginal relative frequencies for the shooter and the goalie are not equal. That's questionable. Here, I might have to come back to that. Row totals are not equal. Which of the following indicates this? So it's not saying are these true, which indicates an association between the shooter's choice of direction and the goalie's choice of direction. I don't think that the goalie kicking left, or the shooter kicking left and the goalie moving left is, I just don't think that proves what they're trying to prove here. The row totals are not equal. I don't think that proves much of anything right there. For the goalie, relative frequency of a direction is equal to the relative frequency condition of the shooter's direction. Okay, so let's choose a direction like left, right? So for the goalie, for the shooter, that's 80 divided by 165. For the goalie, that's 80 divided by 212. Those are not equal, right? For the goalie, the relative frequency of direction is not equal to the relative frequency of the shooter's direction. That seems exactly what this is. So just to remind you what kinds of stuff they might ask. They didn't ask on this question, but they might say interpret this slope. So 0.9 over 1. In the context of the problem, this is 1 is like your x value here. So that's like your height, I think, height measured in centimeters. And the y value is always slope is y over x, right? So the y value is c, which is a cost or something. Collar size, I guess collar size in centimeters. Okay, so what that means is, I know this question didn't ask about it, but to interpret the slope, you'd say for every 1 centimeter increase in height, the collar size goes up by 0.9 centimeters. Okay, so now let's interpret the y. We predict, by the way, the collar size will go up by that amount. The y-intercept, if you think about a y-intercept, oh, that's weird, first of all. That's 0, negative 94 centimeters, I guess. So the x value is that one. So when the height is 0, that's weird, the collar size is negative 94. That makes no sense. The intercept is not meaningful, is sometimes the way we say that. So those are the two things we usually interpret. The other things we could interpret, I guess, but those are the two biggies. And the big thing is the y-intercept doesn't always have a meaning to it. Oftentimes it doesn't. This is actually almost exactly what we call, is this equal standard deviation? It's not, right? This is like we did in the last chapter, really. So the variation or equal standard deviation here, the standard deviation of the hours is not the same across the doses. You can see much less standard deviation here, much more standard deviation off to the right. It's not equal standard deviation, the variation changes is the idea that very much related to our last section here. Following chart displays the relative frequencies by grade level. So here's the thing. We don't know how many 9th graders there are, how many 10th graders. We don't know nothing about the numbers. We just know percentages. So more than 60% of 10th graders, yeah, that's true, more than 60%. So that's true. Which one is not supported? That's true, so that's not it. 12th grade students had the least percentage of students responded yes. That's definitely true. Because percentage, we know. Less than 40% of 10th graders responded no. That's true. The number of 10th graders responding yes was greater than the number. I don't know about the numbers of folks here. The percentage of less graded who know less. Yeah, so that's true. Okay, so it's got to be D. This one, they're asking about this outlier here. Let's just try to estimate it the best we can. So like, I don't know, it looks like 10 is the predicted weight. So predicted weight is 10, so somewhere around here. I know that's either D or C or E. It's below line, so it's not that guy up there. And it looks like, I don't know, that looks like 5-ish. I'm not sure exactly, 5, maybe a little more or less. So 5-ish, it's got to be C. That's it. Number 9. An exponential relationship exists between the explanatory variable and the response variable set of data, the common logarithm. So this is a key to the section. That's the log, right? When x is 4.8. So we're going to plug in 4.8 there and get our calculator and let our calculator cook here. Okay, so we're going to do solve mini 3-1 log of y, I guess, equals 7.3 minus 1.5 times, I'm just going to put in 4.8 there. It should do the work for us. Comma y, the variable we're going to solve for. 1.25-ish. Yeah, that's it. And last question, researchers study a specific type of tree, creates a least squares regression line. There's also shown in the computer output. So this is the slope. So that's 30 over 1. This is the related the height and the diameter, both in the family grown tree. Results are shown below. Which of following represents the predicted change in height? So this is, I think this is h. What's the diameter? So diameter, this is always the x variable listed there. So this is diameter. This is height. So for every 1 meter increase in diameter, well, that's the slope here. The other one's going to increase by 30. So it's just a matter of figuring out the x. The x value is always listed here. The other one's in the context of the question.